All right, well, welcome. I'm going to go ahead and get going, just talk a little bit about compression. One of the reasons this has become important is something we see a lot, really in the community and in Slack, our community Slack channel. If you haven't come to join that, please do. We're trying to stream every week if we can about a topic, at least once a week. We have a developer advocate team of 4 people right now, and we're growing that team, trying to do a better job at hitting at the problem areas that a lot of users seem to have, some understanding, maybe not fully understanding how it works out within their specific use case. And so compression is one of those things that seems to come up fairly often. It's an excellent tool. It's a really unique and excellent feature of Timescale, particularly with time series data. But exactly how it works, exactly what's going on under the covers, what are the settings that matter? Why doesn't it work like I expect? Why aren't my queries doing what I think they should? All of those are things that we hear often. We see a lot of those questions in the community and on Slack and so forth. So that's what I'd like to talk about today. Now this is a first run through of this presentation. It's actually some new stuff I've tried to put together, and actually taking some slides from an old presentation. We're going to work to clean this up, and we'll do this presentation probably on a fairly regular basis. We really want people to use compression for a number of reasons. It really can help a lot of your historical queries. Obviously, it can save you a ton of money and effort on space. We get compression ratios on data, often 90% or greater. Depending on the schema you have. So there's a lot of real good value. And we just want people to know exactly what's going on and have the right expectations going in. So my name is Ryan Booz. I didn't say that yet. I'm a developer advocate. I lead the developer advocate team here at Timescale. And we'll get rolling. If you have questions, I think some of my other team members will be watching the chat. I'll do my best to do the same. Now, this is streaming both on YouTube and Twitch. I currently am only looking at the Twitch chat, but someone can ping me if we need to. So let's talk about timescale and compression. So what we're going to do today, the goal is an hour. I'll do my best to keep this to an hour. We're going to talk about what compression is, how it works in Timescale. How does Timescale implement the compression? And then I'm going to try and give a demo on a couple of things. First of all, settings that impact compression, right? So when you, that is one of the first things that I think there's some misunderstanding of. Because of how it works, the way that you set it up can really impact how good of a compression ratio you get, and then maybe even how some of your queries perform. And I'm going to try and demo a couple queries that might benefit from compression. And then finally, we'll talk, if we have some time, I might try and look at a couple of the internal tables that are dealing with compression. So that's the goal. Again, this is the first time through this topic in this form. So if you have thoughts afterwards, please let us know. And we'll give it a new update and keep going. Like I said, this is a conglomeration of a couple different presentations that have been done. So there will be some differences in the way the slides are made up. It just is what it is. We'll keep getting better. Here's a quick history of compression in TimescaleDB. So it was introduced in version 1.5. There's a great article about how what we did and how it works. So a lot of what I'll talk about is covered in that blog post, and it's honestly, a couple years old now, but it has a lot of great information. Everything we're talking about here, you'll find in this blog post on our blog. So you can go look at it, building columnar compression in a row-oriented database. In version 2.1, we tried to start to lift some of the limitations. So one of the limitations that honestly had prevented a number of people from even thinking about using compression was that once a table was set up for compression, you couldn't modify the schema. And so it makes sense. You have a time series table, you make a hyper table out of it, and then you realize a year later, there's some new information you want to track. And the only way to do it was to decompress all of the chunks, which maybe you couldn't do now, and update the schema and so forth. So another option was maybe you would create a new table with a new schema, copy all of your data, recompress that, and so forth. So it wasn't the best user experience. We knew that. We knew we needed to continue to make improvements. And version 2.1 allows you to actually modify the schema now. Version 2.3, which was released about 2 months ago, back in May, actually allowed you to now insert into a compressed chunk. So you'll see as we go, you create a hypertable, you set up a compression, and again, there is some expectation you have a little understanding about hypertables with this editing. You know what I'm going to do? I'm going to quickly turn on night shift. I can see the glare on my glasses, and it's bugging me. So why can't I think of what I need to do here? Man, sometimes Mac system preferences. I apologize. It just bugs me when I look at the screen, and because of my reflective glasses, it tends to do better. Okay. There we go. I don't think that will impact what you guys are seeing, but for me, it will make the glare a little less obvious on my glasses. So then in 2.3, we allowed you to actually insert data into hypertables. So the reason was, again, when you'll see as we compress data in chunks, it really makes it immutable because we take something that is rows and we make it into columns. And so to insert now into the middle of those arrays of columns, it really is difficult, quite honestly. And so we didn't allow that at first. With version 2.3, we allow you to now insert into tables historically. So if you have tried to use timescale and you weren't willing to do compression because you couldn't insert historical data, hopefully this is another reason that you would start to try and think about doing that. Now, there are a few limitations. You can't update and you can't delete data yet. Again, we're slowly getting there to the things that make the most sense right now. So that's the history. And so what does this mean? This is what a logical definition of your table looks like. If you're using a database, this is what you would expect to see, I would assume, right? We have rows and we have columns. That is what a row store SQL relational database typically looks like, whether it's Postgres, Timescale, which is built on Postgres, MySQL, SQL Server, Oracle. The basic tables, time and again, are built as a row store definition, right? And that means that the things you get with that is that they're indexable, right? So you can actually create index on specific columns to help your queries be faster. They allow high concurrency for small reads, right? So you get lots of data. For every row read, you can get every column. So you can get a lot of data out for small chunks pretty quickly, particularly if they're all within similar pages and things like that. The problem is when you want to do aggregate. So I want to get an average of a column or a couple of columns. Generally, in most cases, depending on your indexing, you're going to end up being IO bound because you need to select all of the rows and get all of the columns still. And then the query planner grabs the columns out of the rows. Then it aggregates them together through usually some kind of looping mechanism, what have you. It becomes an IO issue and something you need to think through. And then there is per row overhead on transactions. And so that's just something to recognize. It's a transactional database. You're getting the benefit of transactions, and sometimes depending on what that might look like for inserts and so forth, it can be a little bit more overhead. And the other problem with row stores is generally they compress pretty badly. So really in Postgres, the only way to compress data at this point is using native on-disk compression. So ZFS compression, depending on how your schema is set up, depending on the page orders and so forth, you can sometimes get 3 to 7 times compression, less, more, what have you, but there we go. And then, while this did not work out, I had to change the format of the slide, I realized, right beforehand. We're going to see another version of this, so do not worry. This is really a copy of this, which is just to show, I'll just zoom in here instead, that when we apply compression, so we have the row store, and when we apply compression, we end up with one row, and then each column is stored separately as an array. And so that's something we're able to do if that is what really converting that single row into a column store would look like. And so it's what we're trying to do ahead of time. So the benefit of columns, and this is why a lot of more high performance databases you're seeing nowadays, tend to be column oriented. You can aggregate and scan columns really effectively, right? So now if I need an average or an aggregate of one column, I can just get all of the rows, all the values for however long the range of time is for that one column. I didn't have to get all of the other data. And that's a really effective and efficient way of getting your data. So it's really efficient to do aggregates this way when you're doing a couple columns. It's also really compressible, right? So if I have one row with many, many items, all of the same type, I have a number of compression algorithms I can use to try and get the best compression on that data. The couple of downfalls are restructuring the entire row gets more expensive, right? So now, rather than getting one row for a select, I now have to go select individual columns, decompress them, find the row that I'm trying to select, reconstruct it into a row and give it back to you. And that just takes more resource when you're trying to get a lot of values for a few number of rows. So per row updates and deletes are expensive or honestly maybe not even possible. And then indexing is always coarse-grained, right? If I have a bunch of columns that are array-based, so if I have this kind of column, and now these are arrays, it's not really easy to index arrayed columns. You might be able to do ranges, mins and max, things of that nature, but I can't say, in the middle of this array, there's exactly the value you want. That becomes really difficult. And so that is one thing that doesn't work really well with column stores. So, row stores are really good for whole row queries. They're indexable. You can update them. You can delete them. Lots of things there. Column store is really good for single column aggregates or, a couple of columns. Statistics where, you need to get something about a column. What is the histogram of this column for some period of time? Again, as long as you're doing a small number of columns. And then typically, column stores are smaller in size because you can compress them much more easily. And, we recognized as we were thinking about this a couple of years ago, how we're going to implement compression, this really trends very well towards a couple of specific data uses, right? So row store data works really well with newer data. So the data that's coming into your application, the stuff that's right now that you need to insert at high rates, you might need to update it within a certain period of time. That works really well for row store. You get indexes, things just work really well. You need to see across the whole system for a shorter period of time. It's a perfect use case for row store. And it is actually something that column stores don't do very well at when you need to get lots of stuff over shorter periods of time because you need to reconstruct all those rows. But column store, again, thinking about how to implement compression and timescale really makes sense for older data, right? So things like, I know this data isn't going to change, so I don't need to worry about deletes and updates. And generally, I don't need to now see the specific value of every column right now. I might want to say, hey, the current CPU is X. What is the average CPU over the last month? So I'm getting the average of one column for historical data to compare it to something recent. That's a great use case for column store because I can get thousands and thousands of values really quickly, aggregate them, and get a response back without having to select all of the other columns. So that works really well. And I should hide myself. Oh, I don't have that one set up. It turns out the PowerPoint I was using just wasn't set up for wide format, and I did that right before I went to stream. So I had to reorient my screen. Apologize for that. All right, and so how do we do it in Timescale? We try and make it transparent. So there are functions you can call manually, and you can set up a policy that will, over time, if you think about these as chunks underneath the hyper table, the ones over here are newer, so we're not going to compress them. But as the data ages, maybe it gets a week or two old or a month old, and we start to compress it into columns. That really allows you to use the benefit of both generally for how time series data is used. All right. So it reduces the storage size. It allows you to maintain ingest rates, right? So if you're ingesting into the uncompressed tables, you can insert data much more quickly. Both of these reuse the Postgres storage. I'm going to talk about that in a second. And again, since we've implemented it as part of Timescale, you don't have to think about whether the data you're getting is coming from a compressed table or an uncompressed table. You execute a query, we'll go find the chunks, whether they're compressed or uncompressed, to get the data out of, and we will then append them together to give you the final result. And so within a database, again, this is what we've been talking about. It's kind of like we are moving towards what we really consider a hybrid method to really serve both of these query and use cases well, right? Inserting data, querying near-term stuff out of uncompressed chunks, and then querying historical column data out of compressed chunks. And so what we did is we basically took our rows, and what you'll see, and as we showed briefly in that blog post, is we then take up to 1,000 rows for each column and in a chunk, and we compress it. So we take all the data in that one column, and we now transpose this into one compressed row. So we have one major compressed row. That row now has individual columns with compressed values for up to 1,000 rows of that column within that chunk. And so again, since they're all the same data type, we can apply specific compression algorithms that work for that data type. And then one of the questions might be, what happens, and I already showed this looks a little bit better. We have our row data up top. Once it's compressed, without any real settings, all of these values become arrays, for each item. So what happens if the page won't fit on disk? What happens if you have a text column and we can't fit 1,000 items in a column on a page and what have you? Well, this is where we take advantage, and this really is I hate to say secret sauce because it's not really secret. This is how we do it in Timescale, is we'll take any of those things that don't fit within the page. Most of these things, we actually save them out to Toast. So Toast is the oversized attribute storage technique within Postgres, which is a way to take data that's too large for a page, saves it in a different location, and we simply point to that data. Well, that also means that the actual table gets really small and really fast and easy to scan, particularly when you only need to find the individual columns. And so that's how we do a lot of our work. We actually take most of the data you compress, bind it up into smaller column arrays, and then when they get too big, we save them out as Toast files that we have a pointer to. And so, it doesn't matter how these work. This is really the compressed row, the logical representation. And anytime it gets sent out to Toast, that column is actually just a pointer out to the Toast file. That also means from a retrieval perspective, like I said, if I say, give me column X for this time range, it might only be 3 pointers, right? So there's only 3 rows that represent thousands of values, and I just have to go get 3 Toast files to merge together, uncompress, and work on. So it's a very effective, very efficient way of working with your data. Don't use PowerPoint, open source for the win. Thanks, whoever that might be. Secret Toast. Yeah, that's true. Secret sauce. I'll be honest. Yeah, the PowerPoint I'm using was already in Keynote, and I actually like Keynote for a number of things. So thanks for the suggestion, though. Hybrid store is like a column store. So again, we don't call this a hybrid store, but that really is what it is, right? So the heap, the actual table that you're now querying, the hyper table, those compressed chunks, are just really, really small now. It may have gone from tens of thousands or maybe millions of rows to a fraction, up to a fraction, 1,000th of that number of rows if it compressed really well. So scanning a single column is efficient and compression is efficient. So here's how we compress. Again, this is all in the blog post I showed earlier, and I'll show it again before we leave, before I switch over. Integers and timestamps, we do delta, delta, and or simple 8-bit. And again, you can read how we do that. Floats, we do gorilla compression. That's something that was devised by Facebook. And then everything else, we do a dictionary array. And what that means is if the column has a low number of repeated values, so maybe you have metric. We often talk about metrics. So you're measuring temperature, CPU. So you have a narrow table format. So maybe you have a date, time, a value, and what that value represents, temperature, CPU, what have you. If that column has a low number of items repeated over and over, we detect that. And what we end up doing is a dictionary. So we'll say, oh, here's 10 values. We'll create a dictionary for those 10 values and replace the text, which could have been larger, with that lookup index. And so we can get better compression that way as well. So a number of ways we do that. There have been questions, will we allow people to customize the compression for different columns? I think there's even some issues for that in GitHub. You're welcome to give your own opinions and see what that might look like. And it's something we definitely have talked about. So give your input, create an issue if you need to. So the two things that we do is we allow you to, you'll see in a minute, there are a couple settings for setting up tables. So one of the other things we recognized, when you are then compressing values, if all of these rows are the same in a table, I have device 1 and device 2, and they have drastically different readings. One is on the order of 0.1, one is on the order of 100,000. So they're just much bigger. When you're doing delta delta, if these are row after row, you end up getting less efficient because you have to track the delta between 1 and 1,001 from one value to the next. And then 1,001 back to 0, and then 0 back to 100,002. That's not really efficient. And so one of the ways you can get better compression depending on your data is you can help us choose to order some of your data a little bit differently. So this helps within that chunk getting a little bit better delta delta between each of those values. So that can also help. When you do that, when you give us an order by, we actually then track the min and max of the columns that we are ordering by as well. We'll talk about what the defaults are and how you might be able to do something different. And then you can also segment by. That's the other option that we talked about. And segment by is really valuable, particularly when you know that an index would really help. And so I'm going to show you why that matters. But essentially, you can order by something or you can segment by. So order by gives you the min and max. We'll track the min and max of that order. When you segment by something, we actually create an individual row, compressed row, for that segment within that chunk. So let's say you're tracking sensors, sensor 1, 2, 3, 4. If you segment by sensor ID, you will now have a row specifically for sensor ID 1, however many rows fit within that compressed table. If you have 2,000 readings in that compressed chunk, you would end up, in theory, with 2,000 rows, with 2 rows with 1,000 readings each for sensor 1. And then sensor 2 would have 2 rows for 1,000 readings for sensor 2 and so forth. That's what segment by does, and the reason we give that option is you can actually do indexes. We can create indexes on those segment by columns. Now it can help or hinder your compression, right? If you segment by too many things, then you're not compressing by as many rows and values in each column. Something to think about. So this is what segment by looks like, similar to the old one, the one I showed a little bit earlier. We have the rows, I segment by device ID, and now that device ID is not an array anymore. It's actually an individual value. We create an index on it, but all of the other items in that are arrays, and by default, they're ordered by the timestamp unless you tell us differently. So the last big thing before it gets to a demo then, so that's the basics. There's a lot there, and again, as I said, I know that these slides need to get updated a little bit. I was trying to take from a couple older presentations to help. I've been seeing a lot of questions recently, and that's why we wanted to start to tackle this. I think the one thing that can be easy to forget sometimes, though, is that compression happens on a per chunk basis, right? So when you create a hypertable, I'm going to show you this in a minute, you tell us a chunk time interval. Let's say it's 1 week. As I insert data, every week of time, Timescale will create a new chunk for the next set of data, the more recent data. And when you compress data, you're only compressing what's inside of that each chunk. We don't reorganize the table. We don't go cross chunks. We're still keeping it compressed per chunk. And so you're ordering, your segment buys. You really need to think about this in terms of what does this data honestly look like on a per chunk basis, right? If you have low cardinality in each chunk, maybe you didn't select the right chunk time interval, and so you only have 50 rows per chunk per device, you're going to get fairly inefficient compression. If you have 1,000 or 5,000 rows per device per chunk, because it's a longer chunk, you'll get better compression in theory. And so it's just something to recognize. I think that can get lost, that what you're looking at is the way the query executes, it's against the chunk. How does the ordering impact the chunk and so forth? So I'm going to try and do a couple demos here. Hopefully this will help bring some of this home. The first demo data set I've been working on just the last 24 hours, trying to give you something to play with to show you how compression is impacted by some settings. I have 200 fake trucks. The data here is very random, just created by generate series. You're actually going to see how that can impact compression. Each truck reports readings every 5 minutes, so 12 times per hour. And I created 2 months worth of data starting from today. And so there's about 3.5 million rows in each of these tables. They are copies of one another, and you'll see why in a second. And then demo data set 2, I got set up, but I haven't had a chance to compress it, so if I have time, I'll do that. This is the data set that we use when we benchmark databases. It's from TSBS, that's the time series benchmarking suite. I just did it for 100 hosts, readings every 10 seconds, so that's 360 per hour per host. And I did it for 30 days. So I think I did it for 30 days. I ended up getting more than 103 million rows. So I must have messed a setting up somewhere. But we have over 100 million rows to play with there. So hopefully between those two, we can demonstrate a few of these queries and help you understand where the benefits lie within each of them. So let's go over to dbeaver. So this is the tool we tend to use. Just to demonstrate stuff. It's a little bit easier for me to show, just to see stuff. I prefer the coloring, so you can see how the queries actually look and so forth. So as I said, I set up a number of tables. So truck log, I then have a truck log 1 day table. It's a copy of the other one, so it's just truck log 1 day. And then I have a truck log 6 hours. So it's the exact same data. So what I did is I created that first truck log table. I inserted 3.5 million rows. And because I didn't change any settings, I created that hyper table. It means that the chunk time interval is set to 1 week. So Timescale will create 1 chunk per week as data comes in. And when the new week starts and I get a reading for that week, it will create the chunk and keep going. So we can see that for truck log, I'm using a timescale function called showChunks. I have 9 chunks for this table. Right, starts at this chunk. This is the underlying chunk that's part of the hyper table. And to get a sense of how many rows per truck are in a chunk, I just selected a chunk in the middle just to make sure it was a complete chunk of data. And I'm just going to do a count. So you can actually query chunks. Again, we'd never recommend you do this for anything specific. You're bypassing Timescale's query planner when you do this, but it's more for me to show you what's happening under the covers. So we have, I think I have compressed these. So let me uncompress them real quick. I was playing earlier. All right, so when you compress a table, you'll see that the actual hyper table now, the actual chunk doesn't have the data you expect it to have. There's the values aren't there that you would expect. So how many rows per truck per thing I'm measuring? So in general, there seem to be a little over 2,000 rows per truck per chunk. So it means I got 2,000 readings per week based on the data I inserted for these trucks. Now, when I query for something like this, I actually also created one index on truck ID, and I believe I created an index on truck ID and time descending to demonstrate skip scan a little bit. So when I do that, I can query this. I'm getting the average weight of every truck. There's 200 trucks over the last 2 weeks for 10 of the trucks, and so certainly wasn't slow. 37 milliseconds in total. It did read 4,000, a little over 4,000 pages of data. So that's the physical, it's all in memory, but there's 4,000 pages it had to actually examine in some way to get the data out of it. Again, because it's in row form right now. I haven't compressed it. And then I set up compression on this table. So this is the way that you enable compression. Now, when you enable compression, you're not actually compressing the table. You're simply telling TimescaleDB when we tell Timescale to compress the table itself, whether it be manually by chunk or through a policy, so that it happens automatically on a schedule for you. This is the way you're supposed to compress it. So in this case, I'm going to segment by truck ID, and that means that I'll get an individual row for every truck ID. Up to 1,000 rows of the other data will be compressed into each row. And in this case, I would expect about 3 rows per truck per chunk. Remember, there's a little over 2,000 rows per truck in each chunk. So I'm not going to guarantee it's just 3 rows, but I would expect about 3 rows. And so that's what I'm going to tell Timescale to do. And I'm going to order by time. Now, I did that because I've been playing with this. You have to then actually always set an order by. If you don't specify it by default, it will order by the time column. That's just what will happen. And then everything will get ordered by the time and set into arrays. Now I'm going to go ahead and compress all the chunks except the most recent week. And so there are, what did we say? There were 9 chunks. I will effectively compress 8 of them. Now on this instance, this doesn't take terribly long. I think it takes maybe 10 seconds. Even less than that, it took 5 seconds. So all of my chunks are now compressed except for the most recent one. And I created a little function before this stream to basically spit out what is the current compression ratio. So in this case, of the 8 chunks that we compressed, before those 8 chunks were compressed, they comprised 320 megabytes. After compressing those 8 chunks, they now comprise 74 megabytes. That is a 76% compression ratio, 4.3x. Now we advertise 90 plus, and that is really truthful. We see this time and again in many, many clients. Really, the one reason that this isn't compressing as well is because I'm creating random data. So every row, again, it's ordered by time, and every row has a random value that can be, many values apart. In most situations, when you're querying, time series data, or you're saving time series data, there is at least some form to it. You're creating an incrementing value of something over time. You're creating a reading over time, and if it's CPU, CPUs don't often go up and down and up and down and up and down and up and down. Now, sometimes they do, but often it's in some form or fashion. And so the values, the delta ends up being more realistic, and you can get a better compression rate. So most of our clients, honest to goodness, most of the users that we see usually approach 90, if not 95% compression on a lot of their time series tables. So that's one reason this specifically isn't compressing as well. It's just the randomness of the data, even with delta, and then some of these columns are double precision. So they have decimal points with different precision. Gorilla sometimes is not as efficient, again, particularly because it's very random. So what has happened under the cover? Well, let's go see. So I created a hypertable. This lists all the hypertables I currently have. And if you look, I now have 2 compressed hypertables. I didn't manually create them as hypertables. I set up compression on the hypertable and then said, hey, go compress these chunks. And so what Timescale did is it created a compressed hypertable. So I can look at, this is the truck log row, and I can see that its compressed hypertable is 37. So I can now look at what that compressed hypertable looks like. Now this compressed hypertable is like the interface into the compressed chunks. So I'm not going to go look at the compressed chunks individually. This is the next level of interface. Again, you would never query this directly. Timescale takes care of that for you. But when you query a hypertable and we need to get values out of a compressed chunk, we know where to go and where to do it. So I'm just going to look at the first 5 rows, and hopefully this is what you would expect. I did a segment by truck ID. So I have 1 row per truck ID. I have multiple rows per truck ID because there were more than 1,000 values per truck. And so all of the other columns are in array form and then compressed with the appropriate compression algorithm. So that's why you can't actually see what the values are. They have to become decompressed, which is why you really need to do it through a regular query. So timescale will kick in there. You'll see all the columns here are in compressed form. Going back to that example in the web, again, this is what's happening under the covers. We're then just compressing it given the right compression algorithm. So this is the representation you see. And then at the very end, remember I told you, whenever you specify order by, you actually get these additional columns, or we create these additional columns to specify the min and max for every order by column that you tell us to order the data by. This allows Timescale to use indexes if you have a segment by. So if you query by an indexed column, we'll use that to narrow down the rows. But then we can say, oh, we got all of the trucks for ID 1. We got all the rows for that truck, but you only asked for the time between these ranges. And this allows us to then filter on these quote unquote hidden columns, these metadata columns. And so anytime you do an order by, we will create these mins and maxes to help us narrow down, presuming you're going to filter by those columns as well. Now, the other thing that can be confusing to people, so let me just review very quickly before I do this. I had a hypertable. I inserted 2 months of data. I then told Timescale how I wanted it to compress. Nothing happened yet. It was still just a regular hypertable ready to be compressed. I then manually compressed this table saying get all the chunks older than 1 week and go ahead and compress them. This is a simple query to do that. Now, in production, I would set up a compression policy so that it compresses the chunks at an appropriate interval. Now, the entire chunk has to have the end date of the chunk has to have passed the interval that you set here, right? So it is actually finding, it will only do that in a compression policy, really on chunks that are older than a specific time. And you'd want that to be at least older than the chunk time interval so that you're not inserting really high throughput data into a compressed chunk. While you can now insert data into compressed chunks, there is more overhead. So we still recommend leaving the most recent chunks uncompressed. All right, so I did that. We saw the compression stats. We showed you what the hypertable, the new compressed portion of the hypertable looks like. And now let's examine the actual indexes, because this is the other piece that seems to be confusing, and understandably so. I will admit that. If you're not expecting it, it can be confusing. So here are the 3 indexes I currently have on that truck log table. It has an index for the truck ID, for the time, and then it has one for both truck ID and time. Oops, that is not what I meant to do there. Down here. And the reason I did this is to demonstrate in a little bit that we have this new thing we released also with Timescale 2.3 called skip scan. And so one really common thing that you need to do with time series data is find the most recent value for every item. So in this case, maybe I need to find the most recent temperature for every truck in this log table. Well, if you don't have something like skip scan, the way that Postgres works, you still actually have to kind of go across the whole table, do a distinct on it. It just ends up being more work than you'd expect. You would think if I have the right ordered index, Timescale, Postgres would just go reverse order and find that data. It doesn't, and we introduced skip scan, but I want to show you how that can be helpful with a compressed hypertable if you set it up correctly. So remember that we said this is now hypertable 37 because I have uncompressed and decompressed and compressed this table a few times. This is where a lot of people kind of raise their eyebrow. Wait a second. This is the compressed portion of the same table. Where do my indexes go? I have specific indexes on specific columns. Where did they go? And you have to take a step back and realize that you can't, there is no way to index effectively an array of data, right? So we took anything that wasn't segment by, anything you didn't individually segment the row by, became arrays of data. And there's no effective index to help you find an item inside of one of those arrays. It just doesn't work that way. And so we really, what we do is we take all of your indexes, we know that they exist. So when you uncompress the table, they will get reapplied. But in the compressed portion of your table, we only create indexes for segment by columns because those are the only columns, if you remember, that have individual values. It's the only kind of thing that we can effectively index inside of this compressed hypertable, this compressed chunk. So it is something you need to know. You need to recognize that. What is the query pattern for the data that you use? And that will help you determine some of the best ways to set segment by and or order by. Now, the other thing, I don't have an example of this at the moment. And that's the one thing I was going to do and I didn't have time for. If you have a narrow table format, so maybe you have sensor ID and then the metric. What is the value that sensor ID is passing in? So many rows per sensor for a time reading. You probably will create a compressed table. Probably, I'm not going to dictate this. That would be segmented by your sensor ID and the metric. What you'll find is that Timescale will create individual indexes for each of the segment by columns. We don't create a composite index. However, and this is something that most people don't recognize or know, it's not something we have documented terribly well and we're working on that. You can, if it would be beneficial for your specific use case, you can create a composite index on the compressed hypertable. It is a regular table from Postgres perspective. And that index will then be carried through as new compressed hypertables are created. So that has come up a number of times in Slack recently. People have, at least 2 columns in their time series table. It's a more narrow format, something like sensor ID and metric. So for every reading you get in, you have two or 3 or 4 readings for a different kind of metric. And then when you segment by, you lose maybe that composite index, which was really helpful on the uncompressed tables. You can do that here, and that may actually improve your query. So recognize that is possible. All right. Don't see a lot of other questions, and that's fine. I'm just going to keep going here. So recall, this was a 1-week interval, 3.5 million rows. As I said, it's very random data, so it didn't compress as well as I might have hoped, but to be really honest, that's to be expected. So now what happens if I take that same data? So remember, with 1 week of time, 7 days, there were 2,000 rows per chunk. Well, what happens, let's do this. I'm going to take this same. I'll just do it here. It'd be a lot easier and faster. Let's do 1 day. So let me show some chunks for this table. All right, so this is the 1 day. So it's the same number, same exact data, but now rather than 9 chunks, I have 62 chunks. I know it's hard to see down, probably at the bottom. It shows over here, there's 62 rows. It's behind me there. All right, so we get less cardinality. So let me take one of these chunks that I hope is complete. It's kind of in the middle of the whole thing. What kind of cardinality do we get now? So now in this table, every chunk only has 288 readings per truck. Remember, with 1 week of data, it was 2,000. So we've basically decreased that by 7-fold. And so now we have effectively less cardinality per truck, right? We have fewer rows per chunk, so it's not going to compress as well. And every truck only has 288 readings. So, we're going to end up creating overall more rows of compressed data because remember, this is per chunk that we're compressing. So just because I have the exact same amount of data, the same number of readings per truck overall for these 2 months, I will end up creating far more compressed rows individually because I have fewer rows per chunk now. So let's go ahead and see if that impacts compression. So I have 1 day. I'm compressing based on same thing, truck ID and time. I'm going to go ahead and compress everything older than 1 day, so that should get 61 compressed chunks. Again, this shouldn't take all that much longer, maybe 10 or 15 seconds. He says, all right, there we go, about 15. And now let's see what happens with the compression ratio. And so it did impact it. Now, maybe not as much as I would have thought. We started with 334 megabytes. That was a little bit more. Again, we have more chunks, there's more overhead. So there's just more physical space taken because we're creating more chunks. And then it doesn't compress quite as well. It went from 4.3, a ratio of 4.3 to 3.3. So we lost a good 10% or more of our compression ratio. So that's simply because it's not the best chunk time interval I could have chosen. So this is where you have to start to step back. Now, I know this is a question that many people really ask, well, can't Timescale choose that chunk time for me? It's something we keep talking about. There's at least 1 or 2 issues of people asking for this. It is something that you just have to deal with right now. You have to think about your data, how many items, as your system grows, you can change future chunks. You can reset that value, and then as new chunks are created, it will get a new chunk time. So maybe early on in your system, a week or a month is totally reasonable for your chunk time. You only have 200 devices. They report every couple minutes, and then that's great for half a year. And then suddenly you get a big sale. You have 1,000 devices in the wild. They now start reporting once a minute. And so maybe you reduce that chunk time to 1 week. So the newer chunks will then get a little bit better compression overall. And then hopefully you can see that if I do the same thing on the 6-hour table, so again, it's the exact same data, 3.5 million rows, with a chunk time now of 6 hours. And so that just means, let's go back up to the top here. If I do my 6 hours, do my quick math, I would expect this to be, I'm going to choose a chunk in here. Oops. Let's take this. And now I get a measly 72 rows per chunk per truck. So now I'm going to create significantly more actual individual rows overall, because every chunk is going to have to create, it's just going to get 1 row. I have more than, how many chunks did I have here? I have more than 200 chunks. So I went from potentially, I had 9 chunks, 3 rows per chunk, let's say 30, round numbers, 30 overall rows to compress this data per truck. And now I'm going to go to hundreds of rows per truck to compress the same data. And so you'll see that that will impact. Let's go ahead and, we'll do 6 hours. Make sure I have the right one. And again, this should probably take maybe 15 or 20 seconds because there's more chunks I have to compress. And hopefully you just start to see that this is one of the problems that a number of people run into at first. I tried compression. I didn't get great values, and whatever. And I can't insert, so why would I even do this? And you'll see that now it really has impacted. We're now down to less than, just over 50%, and the ratio is only 2.3. So really the goal is to pack as many rows per chunk as you can that's reasonable. Our guidance for, I see how quickly I can find this in our documentation. So where we now test me to see what happens here. So if you go to hypertables, under how-to guides and best practices, my computer is not liking me flipping around here too much. We talk about time intervals here. And so the idea is your chunk time interval setting should hopefully create chunks so that the data you're working with most recently fits into about 25% of your available Postgres memory. So the server memory, when you configure Postgres appropriately, that way it keeps data in memory that you're working with, effectively. It's cached. You're able to access it really easily. And then your compressed tables now become much smaller, and so you can actually fit more of them into memory, but recognize that the goal is not to make really, really big hypertables so that you can hopefully get better compression, into just a few chunks. It really is something you have to think about and work with your data. That's our guidance. And if you do something like that for this data set, this sample data set, if I were working with a year of data, I might increase this to maybe 2 or 3 weeks based on the current set of data I have. I would only have 2 or 3 chunks and I'd still get really good compression. All right. And then as data ages, from 2 or 3 months ago, I'm scanning a really small table. I still only have, think about 200 trucks. I maybe have like 300 or 400 rows I would be scanning through to find values. So it still is really an efficient way to get that data out. And I did want to show here under compression, we do call this out somewhere. It's not always, it's under API. I knew that. So let me go to API. My computer is dragging here at the moment, so my mouse is really having a hard time here. So when you alter compression, we do state somewhere here, so I apologize, I'm not finding it easily, and I need to do that. There is one statement that really does mention that index thing. Again, when you compress a chunk, we remove the indexes, and we create only indexes on the segment by columns. So in the last few minutes we have, I want to show you a couple things. One might be, I'll go back up to this weekly one since it got the best compression ratio. I'm going to go ahead and uncompress the chunks. And again, this is a first go. I'm not going to go much past the hour since I started a few minutes late. We will clean this video up, post it on YouTube as a first go. We'll improve upon what we learned through this, and we'll do this demonstration probably in another month in a similar fashion because this question comes up quite often. So I decompress the chunks. Now I'm going to do something like this. What happens if I don't? Effectively, this is the same thing. Now, if you remember what I said, this is going to have one major difference from segmenting by truck. Otherwise, though, as far as the chunk goes, all truck ID 1s are going to be first, ordered by time and all their values. All truck ID 2s are going to be second, ordered by values. So the ordering is still going to be the same, and we're going to get some metadata values to do filtering on. So I update that. I'm going to compress these 9. Again, it's 8 chunks again. Should just take a few seconds. As far as compression goes, we got, I think it was 4.3. So we actually got we got 4.9. I think it was like 79% compression ratio previously, and we're at 77. So just slightly better, slightly worse, but effectively about the same thing. And really the difference is for some data, particularly when it's not random. Again, I've said this a few times if you're just joining. One of the reasons I'm not getting a higher compression ratio is this is random data. So for something like delta delta, if I have 2 integers, 2 different readings, one over the other, in most cases, your readings don't jump up and down across a wide range. When it does that, you're not going to get as good a compression. But in this case, in a regular system, we generally expect maybe 90% or more. We see it very often. That really is not unheard of. But, ordering in this case for this data doesn't change a whole lot. One of the big impacts, however, and again, we're going to see that this is probably a new hypertable. It is. So let's go find truck logs hypertable. I'm assuming is 40. And it is. So let's go look at number 40 now. And you'll see now, even the truck ID column is an array, right? It's a compressed array. Now that column compresses really well, right? Because every integer for 1,000 rows is the exact same integer. And so it gets really, really small. It's very little to store that. The problem is there's no index. So now if I go look at the indexes, remember truck log has 3, but the new compressed hypertable has no index. And that's because there is no column that I can effectively index because these are all compressed arrays of data. Now what I do have at the end is now I have ranges both for the time and for the column itself that I index. So it almost works like an index, but not quite, right? You will still get a scan over. So if I query by truck ID, I'll still get a scan, hopefully by a time range, and it'll be a little less efficient. But it's, again, that might make sense for the data you're doing. Now, when might that make sense? Well, if you're only, maybe you don't care so much about the ID, you really are looking for things that are, there's a specific reading within your ranges. You need to know if this column or these couple of columns, what the max value is all of the time, right? So you are constantly checking that even into history. It might not matter so much what the ID is. You need to find the max value of that column. Well, that might be a good reason to order the data instead of segmenting by it. Maybe the ID itself doesn't matter so much. Maybe you order by a value and then the truck in this case, so that you're always getting that column out more efficiently and more effectively. That would be a good way to do that. So you still get high compression on the values, but they're ordered in a way that Timescale can quickly decompress that one row, scan from the top down, get your one row and get out, and it's really efficient. So that's one way and one reason you might do that. So let's look. It is now almost 11. I'm about done. Let's just look at a couple things, what happens under the covers. So here's what I'm going to do. I'm actually going to go back to the truck log table. One more time, I'm going to decompress it. So I'm going to get it back all into row store. Doesn't take very long to do. And just to give you an idea of how this works within Timescale. So again, I've been querying these tables directly. I've said this numerous times. I'll say it again. We would never recommend that you actually go to the compressed hyper tables. Timescale itself has built in query planner helpers to effectively find the data correctly in the right chunks, both compressed and uncompressed, so that it will do the work for you. You should never go query the chunks themselves directly. You can't even uncompress it effectively, so don't do that. It's just not worth it. You can, as I said earlier, you can create additional composite indexes if you have more than one segment by column, and there are use cases for that, and maybe we'll look at that in another stream. So this is now row store data, okay? And I'm going to go ahead and I'll just query it. This is for these 4 items, these 4 trucks. I just randomly picked it for all of time. So there's 2 months of data here. Now I had queried this earlier, so it's in memory, so it still is very fast. It's about 82 milliseconds. If I explain it, you'll see, and I analyze it. In fact, let me quickly do buffers here. Now again, buffers show us how many physical pages were read either in memory or off of disk. So to get all of this data, it had to read almost 6,900 Postgres pages of data. It was all in memory, so it's fast. And then it had to go chunk by chunk. It could index scan, right? There's an index on truck ID. So it could find just the rows in every chunk dealing with these trucks. And then once it did all that, it passed those values up and it aggregated it. So overall, it was not slow. This happened in 29 milliseconds this time around. Now, if I compress that data, and in this case, I'm going to compress it. We'll do it 2 ways. First, I'm going to do it by truck ID. I'm going to segment it. So if I know that I'm often going to query older data based off of IDs, this is a really good plan because I will get an index on truck ID to make that query just a little bit more efficient. Then I'll compress these chunks and I'll run the same query. This takes 5 or 6 seconds. So now let me go run that same query. So we're getting the average of one column for these 4 trucks. Again, I'm just choosing randomly 4 trucks. Now, if I run it by itself, I don't know, you'll be able to see it, but that took, it said again, 86 milliseconds. I'm going to explain it, and about 24. Things are now in memory, and this is where, when you do small data like this does get hard to, I should probably try and bust the cache, but this gets hard to demonstrate over and over again. If I do some new, maybe larger queries, you'll see it. But what you'll see here is we were able to, the compressed table was able to do an index scan on that truck ID. Now it only hits 12 pages per compressed chunk, right? It knew where to find individual rows within the pages. And overall, we're down a little bit, and mostly this is because, I'm getting 4 truck IDs across all the pages, and a couple of them are still not compressed, right? So the ones that are uncompressed is where a lot of these pages come from. Now, if I were to do this, let's go back a little bit further. Let's say I now query, and I'll just do this with 𝗥𝗲𝗃, and I'll say where time is less than now minus interval, and I'll just say this is the 1 week table, so I'll say 2 weeks. Right, so maybe I want the historical values for these 4 trucks. Now when I do that with a compressed chunk, it's very efficient. Whoa, what did I do? Oops, I need an and, don't I? All right, so I do that query, and now you'll notice, because I'm only reading from compressed chunks, it's way more efficient. And 26 milliseconds still to do the decompress and aggregate of those things. Now, if I do that same thing on, if I were to do that, I'll decompress those chunks again. Right, so what we're seeing is that Timescale is able to go find the data effectively within each of those. And because I'm asking for one individual column, it's able to read just that column out of Toast and do the aggregate. So now this data is uncompressed, and you'll notice that we're back up in hits, and it's a little bit slower. Now again, I'm referencing individual truck IDs, and so Postgres is actually able to use that index and go get very specific pages. And so the page hits isn't happening all that much. Now the difference here I will show is what wouldn't be good. So now let's do a select star from. I see this happen a lot, people asking this question in Slack. Hey, when I do a select star from a compressed table, it's really slow. Now remember, we said that that's not an effective use of compression. Timescale has to go get every row, decompress all of those columns for all rows, and then reconstruct it back into rows to give back to you. That's just going to be slower. That's not the most effective use of compressed data. That's why other column store databases don't perform well there either. Okay, so be aware of that. So if I do select star from, now as an uncompressed table, it's pretty efficient, right? 29 milliseconds. If I compress this table again, and then I do that same select star, we'll see that it is a little bit slower. 28 is not all that much slower right now. I'm doing myself a disfavor, honestly, by doing this. So let me just get rid of that and run this again. You'll see that we have to decompress all of those things, and it just ends up, live streaming is fun. All right, so now I'm running that query, and that was actually a second and a half. It took a long time to do all that work, whereas if I decompress that data, you'll see that it ends up being a lot more efficient. So this is, again, knowing your use case, understanding what you need to do, and using that stuff effectively. So now if I do that same thing, that took 1.2 seconds. With cache, it would be a little bit less. But again, it's just going to be faster because we don't have to reconstruct everything. So that is some of the ways to think about it. So the effective use for compressed data is really when you're doing aggregates. You'll see significant performance improvements when doing aggregation. So let's do one last thing here. So let me say select distinct. I won't use the other one for now. Distinct on truck ID, and then I'll say star from truck log order by. So remember, I have that descending index, order by time descending truck ID. So because I have that ordered index, and I have 200 trucks in here, what am I doing wrong here? Oops, my bad. Truck ID, time descending. All right, so that was pretty efficient. It got all the most recent readings, and the reason is, if I do an explain, this is with TimescaleDB 2.3 and above, we added the ability to do a custom scan. right? So we do the skip scan. We're able to really quickly go through that ordered index. The problem is if you, again, remember there is no index on that time column when you compress this. So I'm going to recompress this one more time. And you'll see that if I do that same thing, I only compressed everything but the most recent week. Now this is again one of the reasons we asked it. You'll see this is still should be pretty efficient. And it depends on how far back it goes. And you'll see that it did have to decompress some. We were able to custom scan this hypertable. So because I put no limit on it, it still is going to try and go chunk by chunk and find the most recent thing. So this is where you'll actually do yourself, this kind of query doesn't work well with compressed data unless you say something like, you know that the values you're looking for, time, is greater than now, minus interval, and I'll say, maybe 5 days. So I want to see things that have reported in the last 5 days and their query. If I do that, it's a much more efficient query because we can skip scan the most recent chunk, which is not compressed and still has that index. Way more efficient, right? Now, if I do the same thing and I say, is less than, so 5 days and older, it's going to become a much slower query because we have to decompress all the chunks to do that scan and find, where is that most recent value for each of those chunks. That's just something that you're going to be impacted by and know. I'm going to stop there for now. We'll have opportunities to come back, again, improve this. The main takeaways is that, compression works extremely well for aggregates, right? So when you need to do, average X, max, min of multiple columns, you'll get much more effective queries over larger periods of data than a row only store, right? So that's why we often recommend you compress chunks older than a few days or weeks. Again, whatever is your query pattern. If you're doing real-time stock analysis, your data doesn't change after maybe a few days or a week. And you're only ever doing max, mins, averages on older data to do candlesticks and so forth. Compressed data older than a few days. You should never be saying select star from all of time on compressed chunks. Instead, do the aggregates on those compressed chunks. And that allows you to insert effectively. You can still utilize things like skip scan on the near-term chunks that are not compressed. So you really get the best of both worlds by having that hybrid approach. Hopefully this is helpful to get you started. And again, we'll clean this up. We'll post this as something to consume. Go ahead and give feedback, and we can absolutely make this better. Get some other examples. I know that one thing I need to show, and that became clear to me as I was preparing this last night and this morning, is showing a narrow table example. So where you have an ID and maybe a metric of some sort. And so we can do that to show you the comparisons. And again, you'll get better compression by having data sorted correctly with things like real data doesn't tend to jump around a lot. So again, my random data just didn't compress as well because the values are jumping around a lot from row to row. But generally, in most cases, your sensors read, incremental, maybe they go up in value, your number of users per day at a website, whatever it might be. Even stocks. Stocks generally follow a smaller trend up and down. Rarely do stocks go, now crypto's a different story, but rarely do stocks go, $100 to $1 to $1,000 to $1. And so your readings from second to second or minute to minute are going to be much smaller intervals, which compresses better. So I hope that's helpful. We will continue to do this, and we'll move forward on some other topics with Timescale. Have a great day. I think that's about it. Thanks, everyone.